you like lights off or less and fewer lights?
Can everyone see that okay?
Yeah.
I don't think it really matters. Okay, so here's the problem I wanted to start with. About 97% or so, give it or take a few percent, of active climate researchers believe that Earth has been warming over the last century or two, and the humans are significantly affecting the Earth's climate. Okay, so the reason we're warming right now is mainly because of humans. So on the other hand, a recent poll, and this was just a month or two ago that they released this, says that only 65% of Americans think global warming is happening now, as opposed to about 96-97%. And only 46% think that humans are the main cause of the recent warming. Okay? So this is a big divide between the scientists who actually work on this subject and just the general public. And truth be told, as of a few years ago, I would have been in sort of the camp where, well, yeah, I think that global warming has been happening. I knew what the greenhouse effect was and everything, and you can't pump a bunch of greenhouse gases in the atmosphere and not expect some warming. But on the other hand, I would have been one of those who said, well, the projections for the future are based on a lot of complex computer models, and I know all about complex computer models, and there's a lot of ways you can screw that up, right? And so I would have declared agnosticism about the second question. But then, because of some classes, things I want to do with some classes I teach and so on, I decided, well, I better try and learn some more about it. And as I did that, I would have all kinds of questions. What about this? What about that? I did a lot of reading. I have a colleague who specializes in this kind of stuff, so I'd go into her office and grill her for hours on end. And in the end, I came to the conclusion that all of my objections were really, there was truth to them, because there's always truth to things like, oh, there's some uncertainty. Yeah, there always is going to be, right? Yeah, computer models, you can screw them up. Yeah, that's always going to be the case. But what I was missing was a whole lot more evidence, okay, and a sort of consistent framework for talking about it even. And so what I wanted to do tonight is just go through and first give sort of a little framework of ideas for how to think about climate and climate change, and then talk about the big questions like, is it happening, is it us, and should we care? Okay. So just listening to some of you guys talk a few minutes ago about all what you do and everything, and this is probably sort of below some of your level and stuff, but you can go to sleep for a while and then wake up later. And then also, Peter told me no politics, right? So as I go through, feel free to raise your hand and ask a question, stop me if I need to explain something more. If I'm going to cover it later, I'll just say, oh, hold on, we'll cover that later. And then if anyone brings up any politics or whatever, then I'll say Peter. And he has a rolled up newspaper back there. He'll be on patrol. So did you have a question?
Yeah, the question, the first statement there is two parts. Are they both about 97%?
Yeah.
Yeah, okay.
Mm-hmm. Okay, so yeah, that's actually an interesting question in itself. Where I'm getting that information is from scientific polls, where they've clearly defined what they mean by an active climate researcher. And it turns out that as people go sort of toward more and more expertise in the subject, starting with the general public to earth scientists in general, or even earth scientists who haven't published anything much lately, right? To earth scientists who have published lately in any subject, to climatologists who don't really publish on climate change, though, to climatologists who do. And when you get up to that level, yeah, it's around 97%. But as you go through that progression, it gets more and more and more people are convinced of these things. Okay. So, here's how I'm going to give you a framework for thinking about climate and climate change. This is what I call a nasty bathtub model. So you can see I have my bathtub, I have my faucet over there, I have my drain pipe, and there's some hair in the drain pipe clogging it. And well, that's everybody's bathtub, right? But in my bathtub, I also have a ring of hair coating the outside there, okay? So, yeah. So think of very hairy individuals with poor personal hygiene, and that's their bathtub. Okay, so in this bathtub, we have water coming in, right? So that's the source of our water is the faucet. Now when the water starts coming in, well, some of it might splash back out. Okay, so that subtracts from the amount that's coming in. But when it comes in, it's going to start running down the drain. Now at first in my bathtub, the water is going to be running in faster than it runs out the drain. But the thing, so the water level is going to start rising, right? But the speed of the outflow is going to be dependent on like the area of the drain hole and how much water there is above it, pushing down on it, okay? So as the water level rises, the drain is going to speed up, okay? So we have water coming in at a sort of constant rate, and then, so the water starts rising, and the outflow is speeding up. Eventually it's going to get to a level where the rate of the inflow is the same as the rate of the outflow, okay? So we'll call that equilibrium. So it's going to stay at that level, water's coming in, water's going out all the time, but the water level is sort of constant. Now, we have some other things happening here, like the hair in the drain. That's going to slow down the rate of outflow, right? So if we have hair in the drain, well, the water has to get higher before the outflow rate is going to equal the inflow rate, if that makes sense. Okay, so now here's a model of the Earth's climate system that's sort of like that bathtub. We have the sun right there, and then we have incoming solar radiation. That's the small squiggles, because the wavelength of the incoming solar radiation is shorter than the wavelength of the outgoing radiation. Okay, so on its way in, it could just reflect back out into space off of, say, clouds or ice and snow, all that nice white colored stuff that reflects light so well. Now actually the whole surface is going to reflect some light, but that varies a lot. So for instance, a forest or something might reflect only a few % of the light back into space, whereas fresh snow, maybe 90% of the light back into space. Okay, so that's one thing that can happen on its way in. Just like in our bathtub, the water could splash out, and so this is sort of the radiation splashing back out into space. Now, if it does succeed in reaching the Earth and not getting reflected back, it's going to be absorbed by the Earth. So it absorbs this radiation, and then what does it do with it? It re-emits it back out into space, okay, or towards space. Okay, but now the wavelength is changed longer, so it's in the infrared region. So that's why most of the radiation coming in is in the visible light range, so we can see it. But then the Earth doesn't glow at night, because now it's in the infrared range. Even though heat is radiation is coming off of it, it's not in the visible range. Okay, so when it starts emitting radiation back out into space, some of it just goes straight back into space. But other radiation maybe hits a cloud and gets bounced back downward by the cloud. Okay? Or it could be absorbed by greenhouse gases. So greenhouse gases are special gases in the atmosphere that can absorb radiation in the infrared wavelength range. And so they absorb it and then they re-emit it, but when they re-emit it, it goes in all directions. It goes up, back out into space, and it goes downward toward the Earth. So if you think about this in bathtub terms, what's going on is we have sort of a more or less constant inflow from the sun. Some of it might get splashed back out. And then when it absorbs, it's absorbed by the Earth, it re-emits it back out. So that's our drain, is just the radiation going back out into space. But the size of the drain hole depends on how many clouds there are and what altitude the clouds are and things like that, and also on greenhouse gases. So greenhouse gases are like hair in the drain. If we shove more hair in the drain, it's going to slow down the outflow. Now, the surface of the Earth, when it absorbs the radiation, it's going to heat up, okay? And the more, it's going to keep heating up, actually, until it's emitting exactly the same amount of radiation that's coming in. So the amount of radiation that's coming in is going to be just the incoming solar radiation plus the back radiation from things like greenhouse gases. Okay, so the more things like greenhouse gases we have up there, the slower the exit is going to be for this, radiation, and the more the heat has to build up on the surface of the Earth to balance out the incoming radiation. So anyway, sort of like a bathtub. Now, greenhouse gases, let's talk about what those are. So this right here, the first part, these are just gases in the atmosphere, and this is the dry atmosphere. So if we take out all the water out of the atmosphere, this is what you'd be left with. We have about 78% nitrogen gas, about 21% oxygen gas, 0.9% argon, carbon dioxide only about 0.04%, and then there's a bunch of other gases, right? There's all kinds of stuff, and a lot of it we put up there, okay? But in any case, in the wet atmosphere, of course, we're going to have water vapor as well, and that varies a lot by place, okay? So some places, you know, it's really humid, and other places it's really dry. So that varies from about 0 to 4% of the gas in the atmosphere, depending on where you are. But on average, it's more like 0.25% over the globe. Now, the greenhouse gases in the bunch are carbon dioxide, water, and maybe some of these, okay? These other gases. The big three are not greenhouse gases, okay? So, when we talk about the greenhouse effect, what we have to realize is that all of that is controlled by far less than 1% of the atmosphere. So when somebody says, oh, well, what could carbon dioxide do? It's a trace gas, right? Well, yeah, it is a trace gas, but it's the second most abundant greenhouse gas, right? But wait a second, if it's only the second most abundant greenhouse gas, why are we not worried about water vapor in the atmosphere? Why aren't we telling people, no, you can't turn on your sprinklers, I'm sorry? Because, you know, you would be adding to the greenhouse effect. So here's the thing, actually water vapor does account for most of the greenhouse effect, okay? But there's a reason why we're more concerned about carbon dioxide in terms of what we're doing to the atmosphere. And the reason is this: water vapor, if you turn on your sprinklers and add a bunch of water vapor to the atmosphere, it will stay there on average a few days, and then it will condense and come out as you know, turn into a cloud or rain or something like that. Okay, so long term, water vapor can't be a climate driver. Okay, you can't really change the climate in the long term by trying to evaporate more water. On the other hand, other greenhouse gases like carbon dioxide can last a lot longer in the atmosphere. So if we raise the concentration of some of these other greenhouse gases, they're going to stick around for a long time. You know, enhancing the greenhouse effect. Okay, so just to summarize, long-lived greenhouse gases like carbon dioxide, because they stick around so long, they can actually drive climate change. But short-lived greenhouse gases can only enhance long-term climate change that's being driven by something else. So for instance, if I turned up the sun knob, and so there's more solar radiation coming in, that would cause the Earth to heat up, right? But when you have hotter air can actually hold more water vapor, right? So, you can put more water vapor in before it condenses and comes back out. Okay, so the absolute humidity will be rising if you heat it up for some other reason. Okay, so that would enhance that initial push. Okay, whereas carbon dioxide, if you put that in from the outside and it sticks around for a long time, that can actually drive long-term climate change. Okay, so I'm going to talk about some concepts that people use when they talk about climate or especially climate change. So the bathtub model so far, it's just been about why the climate is the way it is, right? But now we want to talk about climate change. What are you going to do to cause a climate change? Now I just talked about turning up the sun, right? So that would be what's called a climate forcing. And a forcing is some outside influence that causes the climate or the temperature to start changing. Now there's positive forcings, and those are things that push the temperature upward, and there are negative forcings, which are things that push the temperature downward. Now in our bathtub, let's think about what forcings would be like. We can think of a positive forcing as being something like turning the faucet up. Okay, so more water's coming in the inlet. Or we could force the system by throwing a bucket of hair into the system from outside. And that hair would clog the drain, slow down the outlet, and that would also cause the water to rise, the equilibrium water level to rise. Now a negative forcing in our bathtub would be, turning the faucet down or cleaning the drain, I guess. In the climate, a positive forcing would be something like increasing the amount of incoming solar radiation, putting in greenhouse gases from sort of outside the climate system. So burning fossil fuels, we're digging stuff out of the earth that's really sort of separated from the climate system, and now we're putting it back in. So that would be a positive forcing, because that would cause the earth to heat up some. Also, you can get greenhouse gases injected in the atmosphere other ways, like volcanoes emit carbon dioxide. Negative forcings would be things like lowering the amount of incoming solar radiation. But also, a lot of people don't know this, burning fossil fuels generates aerosols, so just tiny particles that are small enough that they can sort of float around for kind of a long time in the atmosphere. Some of these are reflective, and they reflect light back into space. Okay, so it's like having more clouds or something like that low down that would reflect more light back into space, or bigger glaciers or something like that. So that would actually cause the climate to cool somewhat. So when we're burning fossil fuels, we're doing one thing that forces it to get warmer, and another thing that would force it in the other direction.
What's their difference? They're not positive in 10% and negative in 10%. They don't equal out.
Yeah, they don't equal out. So carbon dioxide is the bigger forcing of the two. Okay, but it's important to realize that there's multiple factors going on at the same time. So it's not, you can't just whip out a pocket calculator and calculate what the effect of carbon dioxide is when there's more than one thing going on. And a lot of people try to do that. So anyway, they almost universally ignore that right there. Okay, so another negative forcing would be volcanoes can produce these aerosols. So whenever there's a big volcanic eruption, the the climate cools for a few years. Now that's the thing about aerosols. They stay up there for a while, but they come back out eventually. So we're putting sort of a constant stream in there right now. But that's one thing that will happen if we reduce our fossil fuel use. The carbon dioxide will stick around, but the aerosols will come out. And so some of that negative forcing will go away faster than the positive forcing. Okay. The other concept to understand are feedbacks. So feedbacks are processes within the system that augment or diminish the change caused by the forcing. So the forcing is sort of the initial push, and then the feedbacks are things that either keep the push going, or put the brakes on, I guess. Okay, so again, positive feedbacks would augment the push. Negative feedbacks would be what's putting the brakes on. So in our bathtub, let's think about what some feedbacks might be. As the water level rises, which would be analogous to the earth getting hotter, right? Maybe more water would splash out as the water comes in because it's closer to the top of the tub or something. So that would be a negative feedback, right? Because the higher the water level gets, well, the more gets splashed back out, so you're getting less water actually coming into the tub. Another, a positive feedback would be something like this, where when the water level rises, it gets up to my layer of hair on the side, and so some of that hair comes off and goes down the drain and gets stuck, slows down the exit, so that would cause the water level to stabilize higher. Okay, so that would be a positive feedback. The extra splashing would be a negative feedback. Now in climate there's lots of feedbacks, and I'm not going to tell you all of them there, but I'll tell you what the main ones are. Okay, so on the positive, in the positive category, we have things like the water vapor feedback. So like I said, the higher the temperature gets, the more water vapor can fit in the air without condensing and making clouds and precipitation. So that's going to enhance the greenhouse effect, and so cause it to get even hotter than it would have otherwise if this wasn't happening.
Would that also contribute to drought?
What?
There's less precipitation?
Well, as I understand it, the net effect of global warming would probably be more precipitation, average. But there will be places that, but the climate patterns will be shifting too. And so there will be places that get a lot of drought, and there will be places that get way more rain to the point, there's a certain point where you don't want more rain, right? So there will be more extreme events like that on the other end. Okay. So let's see. Another positive feedback would be the ice, what's called the ice albedo feedback. The albedo is just how reflective the Earth is. So if you have a higher temperature, then you're going to melt more ice and snow, and that's your really reflective stuff. And so that makes the Earth less reflected, so more of the incoming radiation is going to get absorbed and not reflected back in space. So that would cause even higher temperatures. Okay, so the higher the temperature, actually, there's a lot of carbon dioxide dissolved in water. So in the ocean, it's if you get a glass of water, it's actually slightly carbonated because there's carbon dioxide in the air, and so it gets dissolved in the water. So it's not enough to make it fizzy, but it's still there, and it actually makes the water a little bit acidic. In any case, if you raise the temperature, it's just like leaving a bottle of soda uncapped on the counter versus in the fridge. Which one's going to go flat faster? It's going to be the one on the counter, right? Because warmer water doesn't want so much dissolved gas in it. And so if you raise the temperature, actually some carbon dioxide is going to go out into the air. And there's also, it's actually a lot more complicated than that. There's some biological processes that generally push it in the same direction. So the upshot is that the higher the temperature, the more carbon dioxide is going to want to go in the air rather than in the water and in the biosphere. Okay. Okay. So also, the more water vapor you have in the air, the more you have more potential to create more clouds. And if they're clouds that are the wispy kind way up high, those ones are the ones that trap more radiation down toward the Earth than they reflect back into space. Okay, so on the negative end of climate feedback, so we have the other side of clouds, and that is that if you create more low clouds, those are the ones that reflect more light back out into space than they trap heat. Okay, and so those are going to be a negative feedback. The more of those you have, that's going to put the brakes on a climate change that's forced in one direction or the other. Okay. Now, also when you pump more carbon dioxide in the atmosphere, some of it's going to be absorbed by the ocean and by the biosphere. Currently, we can track about how much carbon dioxide we're putting in the atmosphere and then how much it goes up every year. And it turns out maybe about half of it is being sort of absorbed by the oceans and the biosphere. Okay? And the other half just sort of keeps building up. Okay? Now, in the same vein, carbon dioxide can also be consumed by chemical weathering of rocks. You dissolve carbon dioxide in water, it forms carbonic acid, which starts dissolving different rocks, and then it ends up as limestone somewhere. Okay, so it's taking it out of the system. The problem with this one is it's really, really slow. So this is important for understanding climate change over millions of years, but for our purposes, human civilization doesn't matter much. Okay? Okay, so now you put all that stuff together, and all those forcings and all those feedbacks, you try and do some bookkeeping on those, and some of the feedbacks are fast, some of them are slow, but when, at least over the time scale you're interested in, when all those feedbacks have had a chance to kick in and everything, you'll have a new equilibrium temperature. Just like when you turn the bathtub faucet up or down, it'll take a while for everything to find where it's supposed to be, and then it will settle out into a new equilibrium. Now, the concept of climate sensitivity is this. We want to know how sensitive the climate is to forcing. If we force it so much, how much is the temperature going to change? So, and this is at equilibrium. So after the whole system has a chance to kick in. Now, this is usually given in units of doubling carbon dioxide. So if you double the amount of carbon dioxide in the atmosphere, how much is the equilibrium global average temperature going to change? Okay, so when people are just talking about climate sensitivity, that's typically what they're talking about. What's the temperature, the equilibrium temperature rise for doubling carbon dioxide? And it's sort of a law of diminishing returns. So if you double the amount of carbon dioxide, you'll get about that temperature rise. You double again, it'll be about the same temperature rise. So even though you're now 4 times as much carbon dioxide, right? So it's sort of a logarithmic function. Okay, so climate sensitivity is sort of the holy grail. All the other stuff and that's sort of all the details. The climate sensitivity is the net result. If we get the exact balance between the feedbacks wrong, that might affect how fast climate change happens or what the details are along the way. But what we're really interested in is what's the net result. After a few decades, where are we going to be if we do such and such to the atmosphere? So this is what everyone really wants to know. This is what everyone really argues about. The other stuff I said up to this point, that's all just standard climate physics, and nobody except absolute crackpots would argue against that, except to say, well, this is a little more complicated or something like that, right? That's just totally off the shelf, out of the textbook type stuff. Now, what is the climate sensitivity? And it doesn't have to always be the same number, but it's probably not too huge a relative to the real answer. That's the holy grail right there. But the problem is, the climate system isn't in equilibrium. Because some of those feedbacks take a long time, because of ocean circulation, it actually takes a long time to heat up all that ocean water, so there's what's called a thermal lag in how fast the Earth responds, the Earth's temperature responds to forcing. And so, like I said, you can't just get out a pocket calculator and look at how much the concentration of carbon dioxide has risen over the 20th century and how much the temperature has risen and then get a climate sensitivity. That's not going to work. Number one, there are other factors going on, like I said, like the aerosols and also whatever the sun happens to be doing and so on. But number two, we're not in equilibrium. So how are we going to estimate this? Because that's what we really need to know. Well, the two main ways to estimate climate sensitivity are using the complex computer programs or computer models that I talked about. And these just basically use basic physical laws to sort of mimic the climate system. And these can be very complex. I mean, they can be sort of three-dimensional and global, you know, much more complicated than a bathtub, in other words, right? They can have ocean circulation and atmospheric circulation all coupled in and everything. So these things can not only predict what the net effect on the global average temperature will be, but they will also do projections of how weather patterns and things will shift in response to forcing. Okay? So that's one way to do it. Okay? But again, we're limited by the fact that we're trying to mimic just modern climate data. It's not an equilibrium. And it turns out that there's a lot of leeway. I mean, that you could have different climate sensitivities for different models, and you might be able to have them fit the data that we have so far pretty well. Okay? So there's going to be a range of climate sensitivities you get out of that. Another way to do it is to use a simple bathtub type model to interpret what's called paleoclimate data. So paleoclimate data, the modern climate data, we use modern instruments and like thermometers, right? So we've been taking thermometer measurements that are reasonably global for maybe 150 years, and that's about it. We had thermometers for a while back before then, but we weren't taking measurements globally, or if they were, we don't have the records. Okay, so with paleoclimate data, what you're doing is you're using things like the density of wood in tree rings. So you know how old that wood is because you're counting tree rings, right? And the density of the wood has something to do with the temperature. So it's a proxy data source. It's not really measuring the temperature, it's measuring something else that you can use to estimate the temperature from. So there are a bunch of these things. There's the tree rings, there's looking at the magnesium-calcium ratio and these little tiny critters that live in the ocean. And then their skeleton things drop down to the bottom in the sediments, and so if you dig up the sediments and you have a way of getting a date on those sediments, you can assign a temperature based on the chemistry of those things. You could do it with different ways with the oxygen isotope ratios in the ice cores in Greenland or Antarctica and other places. You can do it. There's several different ways. But so paleoclimatologists go around collecting all this stuff in as many places as they can and do the best job they can dating all the sediments so that they can line everything up and get global averages for over time. Okay, so the bad thing about this kind of stuff is that there's always going to be problems with assigning the right date. There's always going to be some error inherent in that kind of thing. And getting data that's global in coverage is more of a problem. It's really expensive to drill boreholes and things like that. So in any case, there's that problem with this kind of data. But on the other hand, you can look over much, much longer time periods. So you can look over time periods where you can sort of assume that the system is pretty much approaching equilibrium. So whereas we're picking up some new problems with this kind of data, we're getting rid of other problems. All right, so you know, both of these ways have their pluses and minuses. Okay, so what are these methods, what kind of answers do these kind of methods give us? Now, what we're going to get from these things is not one number, okay? What we're going to get is a probability distribution function. And what that means is that we can get the most probable value, but then we can say, okay, it's 67% likely to be within such and such range, and maybe it's 95% probable to be in this range, and then if it's 5% or less probability, we don't really care. We figure 95% is good enough. So these are I think all either 90 or 95% confidence intervals right here. So from the complex climate models that they use, you get a range from 2 to 4.5 degrees C for doubling carbon dioxide, but 3 degrees C is the most likely climate sensitivity value by that method. Okay, so from paleoclimate data, we can look, say, over the last 20,000 years from the last glacial maximum. So that's when the last time ice sheets were covering a lot of the Earth, and this is so the temperature difference from now to then is about 5 to 7 degrees or so with Celsius for the global average anyway. Now you can do paleoclimate data over the last 420 million years. Many people have done that. For the 20,000 years, it's 1 to 6 degrees. So that's a big range, right? But again, the most likely value is 3 degrees. Okay. The last 420 million years, it's 1.5 to 7 degrees, and the most likely value, 3.1 degrees Celsius. Now, there's actually more ways than this to do it, okay? And one group took 9 different ways of making these probability distribution functions, and they used some statistical methods to combine them, and got a combined probability distribution function. So for these 9 different methods, drum roll please, the final answer is 1.5 to 5 degrees Celsius is the 95% confidence interval. And the most likely value was 2.8 degrees Celsius. So like I said, all of these methods, there's a lot of gray area, there's a lot of sources of error and everything, but you just do the best you can, do the statistics on them, and you can get what the most probable value is. And guess what? It's always about the same, right? No matter what they do, they always come out somewhere around 2.8. I mean, there's this study or that study which will come out with something different, but the vast majority of them comes up with something like that, well, like around 3 degrees. And there's more or less error associated with different things. So sometimes the error bars are going to be wider, and sometimes they're going to be narrower. But this is probably a really good estimate right here, 1.5 to 5 degrees. So just to jump ahead a little bit, for me, just eyeballing things, the I don't care region, right, for climate change is probably anything less than 1.5 degrees, which there's a couple percent chance that that's the case, right? So can you see where I was coming from a few years ago, where I would say, oh yeah, so uncertain, blah blah blah. But when you get into the details, you find out, okay, you can do a decent job of quantifying the uncertainty, and there's really very little chance that I don't care. Okay? Okay, another concept to understand before we go on is weather versus climate and local versus global. Okay, it's really, really common to have someone pop up and say, oh, this global warming stuff is ridiculous because, I mean, we're having snowmageddon here, right? Or it's really cold this winter. Or look at this record of Greenland temperatures, and it's hardly gone up at all, right? So they're confusing local versus global weather, and also weather versus climate, because we're talking about some different things here. So weather is just the short-term behavior of the atmosphere and sort of related things like snow cover and stuff like that, okay? Climate, on the other hand, is the long-term behavior. So usually climatologists will talk about temperature and rainfall, everything averaged over 30-year periods at least, okay? If it's shorter than that, then the problem is that it's chaotic. It's a chaotic system. It depends a lot on the initial conditions, exactly where you start, what the path is going to be that it takes. So that's why we can't predict the weather more than a few days out very well, okay, especially in a given place. But on the other hand, long term, it turns out to be a lot more predictable. Also, local versus global, one thing to realize is that here in Provo, Utah, if it gets colder here, it probably just got warmer somewhere else. And if it's winter here, it's summer somewhere else. Okay, so if you average over longer time periods and larger areas, there's a lot less variation. So just to give you an example, so I live in Orem, and I just picked a date and went to weather.com and found out what the high and the low for that day was. And it was 33 degrees Celsius for the high, 17 degrees Celsius for the low. That's what? 16 degree swing in one day? And you can almost double that for Fahrenheit, right? So about a 30 degree swing in one day. Yeah, okay, somebody's better at math than me. Hey, you're a physics major, all red, right? Raise your name, all red. Yeah, so he's a physics professor. You can count on them to do math in their head, not geologists. Anyway, though, do you get the idea? Huge swings just in one day. But then if we take the global average and over a whole year, from year to year, that's only going to change by about 0.2 degrees Celsius at most. Okay? So it's going to wiggle up and down, but only a fraction of a degree. Okay? So it's much less variable, much more predictable on that kind of scale. And over longer periods than just a year, it becomes even more and more predictable. So that you can, it's more predictable on the basis of forcing. So, okay. Anyway, here's an example that shows temperature anomalies. That's just basically how much the temperature deviates from some average. And in this case, they're averaging over 1971 to 2000. And where you have the red dots, that means it's hotter than the average in 2010. And the bigger the red dot, the hotter it was. And then the blue dots are colder, and so the bigger the blue dot, the colder it was. And you can see that some places, even though there's been climate change happening, so the temperatures generally raised, some places are colder in 2010 than they were in the average of 1971 to 2000. Okay? So the point is that when we talk about global warming or climate change, we're talking about the global average, and locally the situation might be very different. Okay, so now let's get to the big questions. The first one is it happening? And there's people that will question that. They'll say, okay, here are several temperature records for the global average temperature, averaged over every year, okay? Now, people will say, well, there aren't that enough temperature stations where they're taking data from. okay? Or they'll say a lot of the temperature stations, they put next to an air conditioner vent or something like that. Or they put it in this one place and then sort of a city grew up around them. And so cities sort of absorb more heat because all the blacktop and stuff, right? So it would have been getting hotter at that temperature station just because of that. Well, the thing is, the people who compile these global temperature records, they know all that stuff. And they use statistical methods to try and correct for it. Okay, so the question is, are those corrections good enough? So here are the first three on the list here had CRUT 3B, NASA, NOAA. Those are thermometer-based temperature records, just different places on the surface of the Earth, people taking temperature readings. And one of them goes back to 1850, the other two go back to 1880. Okay? And now, as you go forward, so looking at all of those, they use different statistical methods to do the spatial averaging. They use different techniques for accounting for those sources of error in the temperature readings and things like that. But they're pretty similar. They're really similar going along. But you know, maybe some of them are based on a lot of the same records though, so maybe they all have the same problems. Well, since 1979, we've had satellites doing temperature measurements, but for the most part get the whole globe, and they're not going to have any bias towards cities or have any effect of urban growth or anything like that. And guess what? When you plot the pink and green ones on top of the other ones, once again, the trend is about exactly the same, right? With it, if we put error bars on that, they would all be statistically, you couldn't tell the difference between them, okay? And it turns out that just this last week, what was your name again?
Pete?
Yeah.
Carmen.
So Carmen was just mentioning to me beforehand the BEST study, so the Berkeley Earth Surface Temperature Project. So there's a Berkeley physics professor, Richard Muller, and he was really skeptical about this. And in fact, he went around giving talks where he would really say some libelous things about some of the scientists involved in putting together these temperature records. So he was going to go in and do it right, and he hired some really good statisticians and other scientists to work on this problem. They used way more, they came up with statistical methods so that they could use way more temperature stations than the others had, and you know, they just did some different things so that they were able to do that and take care of some of the problems that people had accused the others of having and so on. And guess what? If I didn't have the data here, but if I plotted it, it would be right on top of all the others. So, anyway, right now, from my perspective at least, there really isn't any question about, number one, whether global warming is happening, and number two, that we know about how much it's happened over the last century or century and a half, okay? We have good enough records that we can constrain that pretty well. Yep.
So now one argument I've heard is it is cyclical, so we could be looking at a big cycle here with your paleo data. Can you go back thousands of years, and are there similar fluctuations?
Yeah. You know what? That gets into the question of what's causing it, right? And is it just a natural cycle or whatever? But as far as just looking at how much temperature has risen, and so far, right? And how much, what the rate is so far and stuff like that. If it stopped here, nobody would care that much, right? If it just started going back down again or something like that. But the problem, I'll get into this later, but the problem is if we understand why the temperature is rising, if we keep doing what we're doing, it will keep rising. And if it keeps rising like it is, and just keeps going no matter what the sun is doing, no matter what all these other factors do, that will be very out of the ordinary. Okay, and that's part of the problem, right? That people will say, well, you know, maybe just a natural cycle, and honestly, just from what's happened so far, that's not crazy, at least. Okay, but I'll get into whether it's us that's causing this right now. So if it's us causing this with greenhouse gases, then we're in a world of hurt. Okay, maybe. But if it isn't us, then you know, maybe it'll just go back down again, or maybe we don't have any control over it anyway. Okay, so that's the next question then. Is it us? So here's some of that paleoclimate data you were talking about. These are different estimates of the temperature evolution over like the last 12 or 1300 years. Okay. Now those are all the colored squiggles. And you'll notice, and these use different types of proxies, so different data sets, different statistical methods to put it all together, and so on and so forth. And so you can see, you know, these estimates aren't like right on. So if we're talking about differences of a degree or so, well, there's a lot of leeway in there. But on the other hand, we can see that it's going way up at the end here, right? So since the Industrial Revolution or so, the temperature has been going way up. Now here's the problem, though. It actually started going up before the Industrial Revolution. Okay, it's been going up for, I don't know, 300 or 400 years. Okay, so it's natural to ask, well, if it was going up, what? Maybe it's just kept going up, right? Maybe it's still natural, and we have to realize that there are natural factors going on. Like, we can't turn the sun up and down, right? We have no control over what volcanoes do. So there are all these natural factors going on. Do they explain the whole rise? Now I'm going to show you something. Because a lot of people say, well, maybe it's the sun. These are reconstructions of the sunspot number. So if you count the spots on the sun, it's actually a pretty good predictor of what how much solar radiation is coming out. Okay, and if you look at the shape of that curve over the same time period, it looks like a hockey stick too. Okay, so some people look at that and say, see, it's just the sun. But on the other hand, if you look in the 20th century, okay, the solar output was going up for the first half, but now it's flat, maybe going down a little bit for the last half of the 20th century. Whereas, you know, the temperature was sort of tracking that at first, but then it's just kept going up and up and up, even though the solar radiation has been going maybe down a little bit. And if you keep track of the volcanic eruptions, that should probably have been forcing the temperature down a little bit too. So all the natural factors that we know of would have been forcing the temperature, you know, either flat or down a little bit. And yet the temperature has gone up. Okay. And actually, you know, right around here-ish is right where we had enough carbon dioxide in the atmosphere that we would start swamping the other factors. Okay. So actually, yeah, there is natural climate change. It's just that for the past 50 years or so, 50, 60 years, those haven't been the main factors governing it anymore. But it used to be, okay? Okay, so what's happening, so that's what's been happening to the sun. What about greenhouse gases? Well, like I said, the main one we're worried about is going to be carbon dioxide. Now here's a plot of the carbon dioxide concentration. They actually take drill cores of glaciers, like in Antarctica. This one's from Antarctica. And they can extract the gas out of the little bubbles in there. And actually you can count the layers down, tens of thousands of years at least, to know the age, but then you can sort of use a model for how the ice would squish to get the ages back before that. In any case, you can measure the carbon dioxide concentration, and since carbon dioxide, it's pretty well the same concentration over the whole globe, this will be a good representation of the global carbon dioxide concentration. And you can see that the units here are parts per million, so it's like one part per million is 1/10,000th of a percent, or something like that. So 100 parts per million is 0.01%. Okay, so anyway, we're through all the ice ages, and between the ice ages, when it gets hotter, the concentration goes up. When it gets colder, the concentration goes down. And again, here the carbon dioxide would be a feedback, right? Because the temperature is actually going up and down because of changes in the Earth's orbit. It's not carbon dioxide that's causing this. But then when the initial temperature change causes the more carbon dioxide to come out in the air, it's going to enhance the initial temperature change, right? So they can bookkeep all of that and estimate climate sensitivity of it. In any case, it's fluctuating between about 180 and 280 parts per million. All the time for 800,000 years it's doing this. And then it gets to our neck of the woods, and we're not any hotter. Some of these interglacial periods between the big glaciations, they actually got hotter than it is now, right? But in any case, the carbon dioxide is sort of skyrocketing off the chart right now. Okay? So we are really, really affecting the greenhouse gas concentration. Right now we have about 40% more in there than we did in the pre-industrial period. Okay? So we haven't doubled carbon dioxide yet, but we're on our way if we keep doing what we're doing. Okay, so, but some people will say, well, what about volcanoes? What if it's all volcanoes that are causing this big rise in carbon dioxide and it's not humans at all? Well, it turns out that the human carbon dioxide emissions nowadays are like 130 times as much as the volcanic emissions. So carbon dioxide is carbon dioxide. If we're putting out more into the atmosphere, then it's more us that's causing the rise in the carbon dioxide concentration. But also, you can look at the isotope ratios in the carbon dioxide. Now, if you don't know what an isotope is, it's just like if you have different isotopes of carbon, they just have different numbers of neutrons. So most of the chemical behavior of these things is governed by the electrons, which are all the same for all carbon atoms. But the isotopes, because they're different masses, they will take slightly different chemical pathways. So if you track the ratios of, say, carbon-13 to carbon-12, you can infer something about where it came from or what kind of chemical pathway it went through. So geochemists use this all the time. But in any case, if you look at what the carbon isotope ratios have done over time, this is back to the year 1000 up to the year 2000. They have been steady, 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 and then they've just been precipitously dropping. Well, it turns out that these numbers over here, I'm not going to explain the units, but for fossil fuel burning, you would expect them to be going lower. Okay, so
is it? You gotta explain a little bit. Is that more carbon-13 or less? What should be
less? So
we're putting more
delta carbon-13 is just, it's like the ratio of carbon-13 to carbon-12, and you subtract the ratio in some standard and then divide by the standard.
So you're getting more carbon-12. And we're saying petroleum is more carbon-12 rich because it came from biological sources?
Mm-hmm. Yeah. And then volcanic stuff would make it go higher.
Yeah, because it's just random.
Mm-hmm.
Okay, that makes sense.
Okay. So now you put all, when they do climate models to do projections into the future, they honestly do try and keep track of all the natural forcings and so on. Okay? So for instance, this is a figure that I adapted out of the IPCC report. And Okay, so the temperature over the 20th century is the black line. And it's obviously averaged over a number of years, right? Then the dark gray band is what the models would predict the evolution of the temperature over the 20th century to be if you just took into account the natural forcings. You can see it, it does about as well as the other band up to the mid-century, and then it starts going down a little bit, whereas the temperature is still going up. But that rise in the temperature since mid-century is predicted really well if they add in human forcings like the aerosols and the extra carbon dioxide. Okay? So, anyway, the point of this is the question isn't is it natural or is it humans doing this? The question is how much of each, right? And which way are they pushing? And it's pretty clear at this point that at least for the last half century or so, we're the ones that have been doing it, right? The nature is just not pushing that direction. And it turns out there's just multiple lines of evidence for this. You can look at the shrinking upper atmosphere, meaning the boundary between the troposphere and the stratosphere is raising. The upper atmosphere is cooling, whereas the lower atmosphere is warming. I could go on, but a lot of these things are saying that the reason for the warming is the increased greenhouse effect, okay, which we know we're the ones causing, right? Okay, there's more heat returning to the Earth. Like I said, a lot of this is just saying more greenhouse effect, and we know that's from humans lately. Okay, so the next question, really the final question is, should we care? Because somebody brought up, climate change has happened in the past, right? What's the problem? If climate change has happened in the past, we're still here. Why don't we just ride it out and ride it out in our SUVs, right? Okay, so what I have here is this is a graph from the IPCC report. And we have the global surface warming. The 0 point here on the y-axis is just like the year 2000, I think, or else 1990. I can't remember which. In any case, so you can see where it goes down to the year 1900. It's down to about -0.6 or something like that. Okay, so the different colored bands are what the climate models predict. Over the next century or two, some of them go out to the year 2300, but all of them go out to the year 2100. Now, the different colors are for different emissions scenarios. So the biggest, you can see there's a big range in what the temperature might be in the year 2100, but most of that uncertainty is not in the models, it's in what humans are going to do. Okay, so they use different scenarios. So if the economy goes like this and this part of the world develops like that and so on, here's a scenario of how the carbon dioxide concentration in the atmosphere might go up over that time. Okay, so they use different scenarios just to see what kind of possibilities there are. That yellow one down there, that's just what would happen if we had stopped in the year 2000 and kept the concentration of carbon dioxide in the atmosphere constant for the rest of the time. Even if we kept it constant, it would still go up some because some of those feedbacks are slow and because of thermal lag and things like that. Okay, so with these different scenarios above that, the blue, green, and red, we can see that the amount of climate change since the year 1900 or so could be as low as, I don't know, a little less than 2 degrees, all the way up to maybe a little less than 5 degrees. Okay? Now, if it gets up to, if it's under 2 degrees, probably not that big of a deal. Okay. above 2 degrees, it just gets worse and worse and worse. Okay, so and actually, if you look at our emissions to date versus the different scenarios about how things will develop, we're pegged right at the high end of that. Okay, so far at least, I mean, that's the biggest uncertainty is just what humans will do, how many wars will break out and people killed and so on. So, but so far, you can say that if we keep doing what we're doing, we're probably up here-ish, right? Okay, so now we're talking about a few degrees difference, right? And so, like I said, one day in Orem, Utah, there was a 16-degree swing, right? So why do we care if the world's temperature goes up 3 or 4 degrees on average? Well, just to give you, like I said, the normal random variation from year to year is only about 0.2 degrees or so. Okay, so if we're raising that up, that's sort of a big change. But just to give some perspective, the temperature during the last glacial maximum, when ice sheets covered huge portions of the Earth, you know, New York, all that area just mowed over with huge continental ice sheets. That was only 4 to 7 degrees colder than it is now. 400 million years ago, it was about 6 degrees warmer than now. And it was a giant swamp world, you know, basically, right? And then 500 million years ago, you know, we have about 390 parts per million carbon dioxide in the atmosphere right now. It was 7,000 parts per million, you know, so the Earth has experienced changes over time like this. But here's here's a graph of how temperature has varied over hundreds of millions of years. Okay, so it's gone up and down several degrees. But here's the thing.
I thought it was asteroids.
It depends on which one you're talking about.
Yeah, it depends on which mass extinction you're talking about. In the Earth's history, and even the ones that had to do with, you know, asteroids or something like that, if you track the fossil record there, leading up to that, things were sort of on the brink, and that just pushed it over, right? So even if it's tied to it.
What was the temperature about during the Permian-Triassic extinction, PT extinction? Do you have any idea? Is that 700 million or is that earlier?
Oh, that'd be like 240 or 50 million, wasn't it?
Permian,
Oh,
Triassic,
the
that would be,
Triassic?
that would be about
that would be
250,
280 or so.
280, yeah,
Yeah, 250
So-
in there.
So-
Well, it went high. It was high.
Look
that
what's
was
happening right around then.
It's like 8 out of 10 life forms went extinct, like over
Yeah,
decades.
yeah. So the biggest 5 mass extinctions that the Earth has experienced, it was between like 70 and 90% of the types of fossils that you can find gone.
And your graph doesn't have a very narrow Eocene, Paleocene.
Well, every data point on this is averaged over 10 million years.
Yeah, I know. So the Eocene, Paleocene extinction was extremely narrow, high temperature, 10, 20 degrees Celsius, maybe more.
Yeah.
They had alligators at the North Pole.
That was about like 56 million years ago or so.
Yeah,
so
they lost a lot of big mammals.
This is sort of smooth because every data
They
point is
averaged
10 million years.
But there was an extinction there. That's the point. It was a
Yeah.
temperature median.
Huge temperature spike, you get an extinction. And the point is that, yes, life forms can adapt, but they can adapt better if the change is slower,
Yeah.
right? So if you get rapid changes, they don't like it. You know, like if you think about it, say you have a swamp, right? Well, the temperature changes, and so maybe it would be better if the swamp moved a little bit north. Well, animals, some of them can just pick up and walk over there, right? What are the plants going to do? They can move over there slowly, but not as fast as the animals. So you can really mess up whole ecosystems when you're killing off some of the organisms in the ecosystem, okay? And they can't adapt as fast as other organisms. Okay, so here, this is a graphic from that paper right there. And they're just talking about, okay, what the equilibrium temperature increase from pre-industrial temperatures in degrees Celsius. So 1 degree, 2 degree, 3 degrees, and so on. Now, and what are the risks that we're facing with those different temperature changes? So if it's less than 1 degree, well, we are going to have some problems, right? Hundreds of millions exposed to increased water stress, changes in water availability, increased droughts in mid-latitudes, and increased coral bleaching, so you're going to have problems with coral reefs dying. Increased extinction risk for many species. I can just go down the list, right? But we have all these different problems, and as you go further this way to higher temperatures, all of them get worse. And they start picking up new problems. Like the biosphere might turn into a carbon source. So instead of us emitting carbon dioxide and the biosphere absorbing, you know, and the oceans absorbing like half of that, maybe it'll absorb a lot less, right? So anyway, 1/3 of coastal wetlands lost, blah, blah, blah. The point is, it's a, you know, over here, it's definitely a problem, right? Over here, we're talking about it's really getting bad, and it's in our best interest to try and avoid this, right? Over here, that would explain why I thought I saw the 4 horsemen of the apocalypse on the way driving up here. Right? It could get really bad. And actually, statistically speaking, it's harder to rule out the higher end than it is the lower end. Yep.
So I have a question. If, say, the biosphere did turn into a carbon source rather than a sink, is there a point of no return? Like, if these positive feedback processes keep happening, is it possible to get less carbon dioxide and revert back to the earlier state?
I don't think anybody really knows. Like, he was talking about the Paleocene, Eocene thermal maximum. It's a huge spike in temperature, like 10 degrees or more maybe. All of a sudden, now all of that temperature rise doesn't seem to be explained by just carbon dioxide or solar energy or anything like that. Nobody really knows what
Could
caused.
have been methane from clathrates.
Yeah, yeah. So there's various hypotheses people have made about why that happened and why, you know, we have this huge spike of carbon in the atmosphere there. But it just seems like at certain points, under certain conditions, the carbon cycle sort of breaks down, at least for a while. You know, it can recover over time, but it'll break down and you get some really rapid changes, which, again, rapid is bad. Right. So, okay, one last slide here. Now I throw this in. I'm sorry, Peter. You can get out. Peter's going to be coming this way with the rolled up newspaper.
Just a little.
Yeah, but one last objection people usually throw out is, well, we can't afford it anyway, so we'll just have to see how it plays out, right? So here, usually when people, like if you get a think tank, a free market think tank like Heartland Institute or something like that, for every issue like this, it was the same for tobacco, that secondhand smoke and stuff like that. We can't regulate that, it would just cost trillions of dollars. And then they do it and it didn't cost that much. A lot of times when they do those economic analyses, what they're doing is saying, oh, if we put this tax on carbon emissions or on whatever emissions or something like that, that money goes into a giant black hole and we never see it anymore. But I ask you, I mean, I'm a Republican, for heaven's sake. I have never heard of the government collecting any money that it didn't spend, right? So there's always going to be costs and benefits. Okay, so one argument against sort of switching to power sources like more wind power and solar power and things like that is that the cost per kilowatt hour, at least right now, is usually more than for fossil fuels. Okay, so maybe it'll cost, like coal price right here in the blue, looks like it's about 6 cents per kilowatt hour, okay? And, you know, oil is probably a little more than that nowadays, but it used to be pretty comparable to that. In any case, when you burn fossil fuels like that, it only costs you 6 cents per kilowatt hour. But what it's not taking into account is now that you've spread all this pollution to everyone else around, and you know, carbon dioxide into the atmosphere and so on and so forth, well, that costs other people money in health costs. There's a guy at BYU, what's his name, Arden Pope or something like that. Yeah, he did a lot of studies about health effects of, say, living by a freeway. And they're substantial, right? That's why the houses, and one reason why the houses there cost less is because you will have a lot more health problems on average if you live over there. Okay, so there have been some economic studies of this, and some of them are very conservative, and some of them a little more liberal about the costs they assign to these things. So this MMN11, that's the more conservative type of economic analysis. And the Epstein, that was another less conservative economic analysis. So these different bands of color, the red means costs from air pollution, okay? And the yellow is costs from changing the climate. You notice how small the yellow is? It's not the biggest band in any of these analyses. And then the Epstein analysis, it took into account just the health effects in the Appalachian region caused by mining all the coal they mine there, okay? Which, I used to live there, and believe me, there are some unhealthy, toothless people there. I'm just... I could go this whole time without saying something offensive. In any case, you add those on top of the coal price, okay? And that is the true cost of burning coal. And some of it, the person using it bears directly, and some of it they pass along to everyone else. Now the point is that, well, if we were being fair, we would put all those costs on the people using the coal, right? And so if we put a tax on on coal to make up for that or something like that, the cost of it would be, by this analysis, somewhere around 10 cents per kilowatt hour. And here, by this analysis, it would be over 20 cents per kilowatt hour. And so the thing is that in either case, you know, in a lot of places, the renewable energy is getting down to the range of, you know, 10 or 11 cents per kilowatt hour. And so in that case, it would be, even if you stripped out the effects of climate change, it would be about worth it, right? And you would get rid of all these health effects and so on. If you add in the climate change effects, they could be small, they could be big, they could be bigger than anything that either of these guys would have accounted for, right? We can't rule that out. It's many times over worth it. To switch, to really aggressively try and switch over to those kinds of things. So anyway, that's all I had. So if anybody wants to ask more questions or anything, that's good.
One more objection, I don't think we covered this, is people will say, it's fine if we work on it and do something, but China won't, and so ours will be a drop in the bucket.
Yeah.
Actually, they're ahead of us in solar. That's why solar prices dropped. That is something I follow. At the beginning of the recession, it was $4 a watt. It's now down to $1.50 a watt. Because they did so much solar manufacturing that it right now is probably worth it in a lot of places just to go solar. Because they're dumping solar, essentially. So China is actually going to beat us on this.
Yeah, so they're not sitting there doing nothing about it. On the other hand, they are building boatloads of coal plants too, right? So their emissions are rising.
And so in India will have to do the same thing too.
So all I can say about it is that you know I bet it will be very difficult to hammer out some kind of deal with them. But if we don't, when we're historically, we've emitted way more carbon into the atmosphere than they have, right? So their perspective is, well, why don't you already rich countries sort of take the lead on this? So if we did, then we would, I think the costs wouldn't be that much. I mean, people really exaggerate the costs sometimes, even though it would cost us some to make the switch.
So that's still the answer to people who make that objection.
Yeah.
Yeah, the cost really, if you account for the benefits as well, the net cost is not that much, even though there would be a net cost probably in the short term. And also, how are we going to get them to cut a deal with us if we don't bring anything to the table? We just sort of demand, we're not going to do, if everyone's standing around demanding that they're not going to do anything until somebody else does something, you'll never get anywhere. And also, the other thing is that you can do this incrementally. Nobody's going to do it all at once, right? So if you say, okay, we're going to go so far, how about you guys? And maybe they'll go so far too, and then we can, but somebody has to lead out. And some people are, like Australia just passed a modest carbon tax, it's only $23 a ton, And that was the objection there. There's a few million people there, right? And so the objection there is, what? It's going to make no difference, right? But, Yep.
The American Physical Society, not looking at these other externalities, estimated that the cost per year is like 2 or 3%. And they said people buy insurance policies. If you just looked at it as an insurance policy against the end of civilization, this might be worthwhile. Okay, I said it. Yeah. But I really believe this could lead to really bad wars by the end of the century.
Yeah, if you have people moving around and you have water resources shifting, right? You're in a
Well, and if you're flooding the land, see, I didn't understand, because North America, we grow our crops at a high elevation. When I checked what the rest of the world was doing, it's within a few meters of sea level. So Greenland's going to melt down. That's pretty sure. But if it does it over 2,000 years, we adapt. If it does it over a few hundred years, then the rising water creates a lot of problems.
Yeah. But places like Bangladesh, not
even
not
China,
even that much.
Right there on those, their
hundreds
river
of millions
basins are really low. And Europe is low in most of the places where they're grazing crops. So it could be really bad. And when that happens, well, yes, people say things like, I have nothing to lose, and therefore bad things happen.
I didn't have a question. I was just thinking that maybe we could mingle around and have some. First of all, thank Barry for a very informative